Everyone, welcome back to my channel Ankura Education. Let us start our today's class. In our today's class, we are going to discuss about the basic concepts related to semiconductor physics. So, let us first define what is meant by interstitial atoms. So, intrinsic or pure semiconductors is practically not available, while doping a semiconductor with impurities like pure phosphorus, boron, arsenic and aluminum may not be available. These impurities will themselves contain some of the impurities again in it. So, commonly found such undesirable impurities are lithium, zinc, copper and nickel, etc. Sometimes they also act as donor or acceptor atoms. These also act as donor or acceptor atoms. Such atoms are called as interstitial atoms. Except copper and nickel, other impurities do not affect much. Now let us discuss about the one of the important laws of semiconductor physics, that is the mass action law. The statement for the mass action law is, under thermal equilibrium condition, the product of electrons and holes is equal to the square of the intrinsic carrier concentration, where Ni is the intrinsic carrier concentration. Intrinsic carrier concentration. So, for an intrinsic semiconductor, the number of holes is equal to number of electrons. That means N is equal to Ni and P is equal to Pi. So, we can write it as Ni Pi is equal to Ni square. If we generalize this equation, we get N into P is equal to Ni square. This is called as the mass action law. And this mass action law, according to this mass action law, the product of electrons and holes remains constant at a fixed temperature, and this will be applicable for both intrinsic as well as extrinsic semiconductors, where Ni is equal to At power 3 by 2 e power minus Eg by kT, where T is the temperature in degree Kelvin, where T is the temperature in degree Kelvin, Eg is the energy gap, and K is the Boltzmann constant. K is the Boltzmann constant, and the value of K is equal to 1.38 into 10 to the power of minus 23 joules per degree Kelvin. If we convert that into electron volts per degree Kelvin, then we get K bar is equal to 8.63 into 10 to the power of minus 5 electron volt per degree Kelvin. This is attained by dividing the value of K with Q, where K is the Boltzmann's constant and Q is the charge of electron. This is very important in solving the problems, as well as this is very useful for all kinds of competitive exams. This may be asked several times in the competitive exams. Now let us go for another law, that is the law of electrical neutrality, which is also very important in semiconductor physics. Let Nd denotes the concentration of donor atoms. Suppose that Nd is the concentration of donor atoms. So, as it is a donor, it can give away some electron. As it gives away the electron, its charge becomes positive. So, the whole concentration P is denoted by, if the whole concentration or whole density is denoted by P, then the total positive charge, that is the total positive charge, is equal to Nd plus P. Say this is the total positive charge. This is the equation number 1. Similarly, if Na is the concentration of acceptor atoms, because it is accepting the electron, that means the electron is accepted by the atom, then its charge becomes negative, and N is the charge density of electrons, that is the total number of electrons denoted by n. So the total negative charge is equal to Na plus n. This is equation number 2. So according to law of neutrality, the total positive charge must be is equal to the total negative charge. If we equate 1 and 2, we get Nd plus P is equal to Na plus n. This is the law of electrical neutrality. This is very important in semiconductor physics. So let us denote it as equation number 3. Consider an n-type semiconductor with acceptor carrier concentration Na is equal to 0. That means the number of electrons is far greater than the number of holes. So we can approximate the Nn is approximately equal to Nd, where the subscript n denotes that it is an n-type semiconductor. So we can write it also as Nn is equal to capital Nd. So but we have Nn into Pn is equal to Ni square. Here we can write it as Pn is equal to Ni square by Nn, that is equal to Ni square by Nd. So from this we can have Pn is equal to Ni square by Nd. So this is the concentration of holes in n-type semiconductor. So this is an expression for concentration of holes in n-type semiconductor. Similarly, for p-type semiconductor, the donor carrier concentration Nd is equal to 0 and the number of holes is far greater than number of electrons. So therefore we can approximate the concentration of holes Pp is equal to Na. If we substitute that in Np into Pp is equal to Ni square, we have Np is equal to Ni square by capital Na. This is an expression for concentration of electrons in p-type semiconductor. So from law of electrical neutrality, we can find out the concentration of holes in n-type semiconductor as well as the concentration of electrons in p-type semiconductors. So this is an important law in semiconductor physics. Go to another important concept, that is the Fermi Dirac function. This is denoted by f of a, and the expression for Fermi Dirac function f of a is equal to 1 by 1 plus e power e minus ef by kt. This is an important expression for Fermi Dirac function and this has to be remembered throughout the lesson. So let us take this as equation number star. As we know that K is a Boltzmann constant and T is the temperature in degree Kelvin, EF is the Fermi level. In order to understand the Fermi Dirac function, we should first know the density of the states, that is N of E. N of E is equal to gamma e power half. This is the expression for the density of states of electrons. So let us take this as equation number 6, where gamma is a constant and that is equal to 4 pi by h cube into 2m whole to the power of 3 by 2 into 1.6 into 10 to the power of minus 19 whole to the power of 3 by 2. On substituting the value of m, that is the mass of the electron, and h, that is the Planck's constant, we get gamma is equal to 6.82 into 10 to the power of 27. So in order to understand the Fermi Dirac function, we should know the density of the states first. That is given by the expression N of E is equal to gamma e power half. Very important to note this. This f of E is called as the Fermi Dirac probability function. It specifies the fraction of all states at energy E, that is in electron volts, occupied under the conditions of thermal equilibrium. So according to Heisenberg uncertainty principle, Heisenberg uncertainty principle, the momentum of electron can be uncertain. According to the Heisenberg uncertainty principle, the momentum of electron or a hole can be uncertain. Heisenberg postulated that there is always uncertainty in the position and momentum of the particle, and the product of these two uncertainties is of the order of magnitude of Planck's constant. So he has given an expression delta P into delta X is equal to H. This is approximately equal to H, where delta P is the uncertainty in momentum, where delta P is the uncertainty in momentum, and delta X is the uncertainty in position, and H is the Planck's constant. Planck's constant. So this is an expression for Heisenberg uncertainty principle. According to him, the uncertainty is in the position and momentum of a particle, and the product of these two uncertainties is of the order of H. Now let us know what is meant by effective mass. This is also a very important concept in understanding the uncertainty and about the semiconductors or Fermi levels in detail. So when an external field is applied to a crystal, the free electron or hole in the crystal responds as if its mass is different from the true mass. This mass is called as the effective mass of the electron or hole. So what we can say, this effective mass is not the original mass of the electron or hole. This is the mass acquired by the charge, that can be electron or proton, but this is the mass acquired by the electron or proton under the influence of applied electric field, say that as epsilon. So this is called as the effective mass. By considering this effective mass, it will be possible to remove the quantum features of the problem. This allows us to use the Newton's law of motion to determine the effect of external forces on the electrons and holes within the crystal. So this is also a very important concept to remember. The next one is the Fermi level. This is named after the scientist Fermi. It is the energy state with 50% probability of being filled if no forbidden band exists. In other words, it is the mass energy level of the electrons at 0 degree Kelvin. That is the mass energy level of electrons at 0 degree Kelvin is called as the Fermi level. So here there exist three cases. That means if the energy level is equal to the Fermi level, that is the EF, then the expression for f of E, we know that f of E is equal to 1 by 1 plus e power E minus EF by kT. If we substitute E is equal to EF here, we get 1 by 1 plus 1. So it is equal to 1 by 2. So at T is equal to 0 degree Kelvin, and if E greater than EF, say this is equation, this is the condition, second condition, that is at T is equal to 0 degree Kelvin. If E greater than EF, then f of E is equal to what we have, 1 by 1 plus e power 1 e minus EF by kT. As E is greater than EF, this value becomes positive. So we can write it as 1 by 1 plus e power alpha, and this is a higher value than 1. So this becomes 0. So the value of f of E for E greater than EF is 0. And the second condition is at T is equal to 0 degree Kelvin, E less than EF. This is the third condition, that is E less than EF. Then the expression for f of E becomes 1 by 1 plus e power minus alpha, because the E value is lesser than the EF value. So this total quantity becomes negative. So we are denoting it as e power minus alpha. So if it is a negative quantity, we can neglect this. So this becomes 1 by 1 plus some negligible constant. So this could be equal to 1. Therefore, for E less than EF, the Fermi level f of E is equal to 1. Therefore, we can write it as the Fermi Dirac function is symmetrical about the Fermi level. The Fermi Dirac probability function f of E is symmetrical about the Fermi level EF. So, if a graph is plotted between f of E and E, it is as shown here. If E is equal to EF, then f of E is equal to 1. If E greater than EF, then f of E is equal to 0. And if E less than EF, then f of E is equal to 1. That is, there is no probability of finding an electron having energy greater than EF at T is equal to 0 degree Kelvin, since the Fermi level is the maximum energy possessed by the electrons at 0 degree Kelvin, and F of E varies with temperature as shown in the figure, and it is different for different temperatures. Its behavior changes according to the temperature. So we can say this graph as the variation of Fermi level with respect to the temperature. This is as shown in the figure. So that's it for today. Let us continue our session in our next discussion. So thank you for watching my video. If you like my video, please do like, share and subscribe to my channel. For any doubts and comments, please do comment in my comment box. Please don't miss to watch our next video because it's a continuation to this previous topic. That's it for today. I hope you understood my concept in detail. So today I tried to explain about the basic concepts like mass action law, law of electrical neutrality, Heisenberg's uncertainty principle and the Fermi Dirac function, as well as the Fermi level and effective mass. I hope you understood these concepts well. If you have any doubts and suggestions, please do comment in my comment box, and don't forget to watch my next video because it's a continuation to the today's topic. Thank you for watching my video. If you like my video, please do like, share and subscribe to my channel. Thank you.